So welcome everybody. My name is Lajos Nyéki. I'm work here at IPM and I'm a chief software engineer here, specialized in Android development. And today's topic is about modularization of large Android applications. So first of all, why do we want to modularize applications? It's not that trivial maybe, because anyways in the end it will be one APK or AEB that you release to the stores. So the first idea is that you would like to separate the layers of your application because, for example, you would like to reuse business logic in multiple UIs, multiple platforms. You want to share your data classes with the backend and so on, this kind of stuff. Or you can think about Kotlin multi-platform as well, where you can, it's also a need to break your code by layers. The other idea is that you would like to separate it by features. Why do you want to do that? Because you have a very large application, multiple teams are working on that large application, and you would like to assign each feature to each team with a clear boundaries. And in that case, if this is really modularized, then you can, for example, if a bug comes and you see which code it comes from, you can easily assign to the team which is responsible for that specific feature. Another thing why you would do this is the separation of implementation eras, so like legacy and revamp. Why you would like to do that? Because maybe your task is to re-engineer your application with a strangler pattern, and after the new implementation of a specific feature is live and works well, you would like to just delete the old implementation, which is much easier if it is separated by modules. Or because you need to, or you would like to set different quality rules for the legacy part and the revamp part, like unit test coverage, 80% on the new code, but because the legacy did not have any unit test, you don't want to care about that. And last but not least, to decrease build time. I will talk about this point a little bit more in the rest of the presentation. But first of all, let's talk about what kind of types do we have for modularization. First of all, levels of separation, how we can separate the code. The most trivial is we can separate the code by lines. That's obviously every software engineer first thing to learn. Even when I learned programming, there was a challenge with people that who can write the same algorithm with the least amount of lines. But you know, in production, this is not the case. You use line breaks also to separate your code. But you also learned, of course, that you can separate your code to files, classes, functions, where you have the visibility modifiers. So you can just hide some code if you declare it private from the other parts of the application. And you have then the packages, or in other languages, the namespaces, where you can group your files and mark those as things that are connected to each other. And this is the part until I think it's trivial for every software engineer, but then comes the interesting part, Gradle modules. So you can also create many Gradle modules in your application. And also you can even have separate Git repositories for each modules. So below this line, this is the interesting part we will talk about. And mostly in the rest of the presentation where I will talk about modularization, I mainly will talk about the Gradle modules. The Git repositories is just a little bit different in a way that you don't need to build the other modules, just pull in by version, for example. So there is another distinction, how we would like to modularize, and it is the vertical and the horizontal breakdown. So the vertical breakdown, you break down your application by layers, so UI presentation, repository, data sources. This is beneficial when you would like to share the code of a layer. For example, if you think about Kotlin multi-platform, and the other way is to split your application by features, which you can see here. And you can also combine these two. So for example, you can say that you break down horizontally by Gradle modules, and inside the Gradle module you break up your code by packages, that you have a UI package, a presentational package, a repository package in your Gradle module. And this horizontal breakdown is better for all the other three reasons why we would like to modularize, so the implementation errors, the multiple teams, and the decreased build time. So I will talk a little bit more about sorry, the build time, but first we need to talk a little bit about graph theory. So when we are talking about modularization, then your module graph can be drawn by a directed graph, where the nodes are the Gradle modules or Git repositories, does not matter that much. And the edges are the dependencies between your modules. And the weight of the edges is the build time of the dependent module. So for example, if you see here, we have the B module, which depends on E and F and C. And to build B, we need 12, let's say, seconds to do that. So what we can see in this graph, two metrics. One is the longest path in the graph, which is this one. So A, B, E, and F by the weights of the edges. It adds up as 101. And this will represent our build time, clean build time, what I'm talking about right now. And there is another kind of metric we can use, which is the height of a graph, which is the number of the nodes on the longest path if we don't consider the weights on the edges. That can be an easier calculated value, and it's beneficial because these build times are not usually easy to guess at the beginning, and it can be an easy abstraction to think about the height of the graph sometimes. And here you can see the height of the graph would be at this path where we have 5 nodes. So after this, let's talk about how we can spare the build time. Let's see this simple example. We have an app module, 3 feature modules, and 1 common module. For simplicity, I wrote the build times to the nodes, and this red line is the longest path. So it means that this application will have a clean build time as 31 seconds. So why? The reason is that during the build, first you need to build common, and after that you can build the 3 feature modules parallelly. And this is where we can spare build time, that feature B and feature A can be built while we are building feature C, and that is the gain on clean builds. Of course, if we are talking about incremental builds, there are lots of optimizations in Gradle, so that's not that easy to say how much we can spare in that. But what we can definitely say that if you modify something in feature B, then definitely you won't need to rebuild feature A, feature C, and common module. So these are the gains of modularization. But it sounds very easy, but then came a requirement that somebody needs a feature from feature C in feature B. What would be the obvious thing to do? Well, let's put a dependency between feature B and feature C. Now the problem is that the longest path now is this, and because of that we made the build time 5 seconds longer. Well, these are seconds. It seems small, but believe me, in a very large project it matters a lot. So it's like 16% of a difference just by adding this one line, which is bad. We don't want to do that. So what else can we do? The next obvious choice is let's move everything that is needed for both B and C to common. Now this became the longest path and the build time became 34 seconds. So it steals 3 seconds more. Why? Because we put a lot of code to common. It is much more time to build common now, which is definitely the first thing to build, so that's why it's, again, problematic. So what we can do, what would be a much better solution than this, is to extract the common functionality from B and C to feature D. And then, through an API module, use the feature in the feature C and feature B. With this modification, we did not implement any new code, just restructured it. We spared 2 seconds and gained the ability to use feature D in both feature modules. So this is how important to think about modules and how they depend on each other. So based on what I already told you, you can have most probably an expectation how a build graph would be visible in a large application. Like, for example, this. But maybe the last slide already showed you that this is not really the case. So let me show you a real example. This is something that in a larger application, it is not that large actually, but it's a significantly larger application. This is from one of my projects. And you can see these are the feature modules, and we have a lot of other modules because of optimizations. So we have these large graphs. But how we can tackle with this, it's not that easy than in the first example where you could just oversee the whole thing. So let's see the tools we have. The first thing I would like to recommend is GraphViz. So GraphViz is a software where you can have a easily textual-based description of a graph like this. So this is an example. You need to specify the type of the graph, which is in this case a directional graph, the name of the graph, the nodes, and then the edges, and you can have styles to these nodes and edges. Why is it great? Because this can be generated by code, by a Gradle plugin, for example. And then you just execute a command line command, and you will get the graph in an SVG, and now you can inspect it much better. The other tool I would like to really emphasize is called Module Graph Assert. It's a Gradle plugin that you can use, and it can enforce the graph rules, and also it can help in the visualization. So you can define different rules for your modules, and you can categorize each module. So you can, for example, categorize all your feature modules called feature, or your common API modules as common API, and you can define rules between them. So because we are talking about a lot of teams who are developing this application, we can make sure that nobody will make a dependency which will make the situation worse. And these rules can be enforced build time. So actually what this Gradle module does is, as the first task of your build, it breaks it as soon as there is something that is violated in these rules. So you are early notified that you should not do this, what you want to do. And also, this can generate your module graph in a GraphViz format. So now that we have the GraphViz format, you can, as I showed you, convert it into the SVG. But also, if you are talking about a really large graph, then maybe even visually it's really hard to see what's going on. And for that, we have another tool called Gephi. So Gephi is an application where you can analyze larger graphs. It's not quite that visible on this slide, but there are a little bit slightly less gray nodes as well. Just one of the nodes are selected, and you can see all the dependencies of that node. But the other interesting is you can make any kind of calculations on the graph, and for example calculate a betweenness centrality or something like that, and then you will get an idea about which Gradle module you need to invest some energy to have a little bit optimized build, because that has the most impact on the graph. So after we talked about this, let's talk about some patterns and anti-patterns. The first thing is the bad core anti-pattern. So you can imagine we have two features, feature A and feature B, and we have some common functionality which we put into this bad core called module. The problem is that in this module, 50% of the code is used only by feature A, 40% used only by feature B, and 10% is truly shared. So the problem here is that we cannot really optimize this 90% of this core. If they would be in feature A and feature B, then they could be built parallelly. So to fix this, we should move this code to feature A and this code to feature B. This is easy if you are thinking about two modules, but the catch here is if you have many modules, this shows that that's why you should not have one common module for all the feature modules, because usually not everything is common. And when you try to put everything into the one module, then you end up in this 10% truly shared code, which you want to avoid. The other anti-pattern is dependency hub. So when there is something in the graph where you have incoming dependencies and oncoming dependencies, I mean many incoming and many outgoing dependencies, this becomes a bottleneck in the build time. So what you would like to do is eliminate these from the graph, and if you cannot eliminate, then at least try to reduce the build time as much as possible. The other problem can be that you have too many modules, which is quite a little bit contradictory what I already said, that you need more modules, but the important is that you need more modules only if you have a good reason to that, because every module has a build time impact. So if you have a good idea why you need to create a module, then it's fine. But if just for why not, that will cost you. And also large modules are fine if those have just a few dependents. For example, feature modules can be larger. It's not that much of a problem, the direct dependencies of the main app module. So let's see how two modules can, for example, two feature modules can communicate with each other. For this, we have the dependency injection pattern, which most probably everybody knows. But here the idea is that the dependency injection configuration lives in the app module. In the common module, there is an interface for one of the functionality, and class A needs class B, but the app module provides during the DI configuration through the interface. If you have multiple modules, then also it is a good idea to use composite design pattern. Sorry. So in this example, we have an application where we have a profile module and a booking module, like, for example, hotel booking or plane ticket booking, whatever. And in the common view, have a login listener interface. So booking needs to know that the user just logged in or not, maybe because there is a background service that needs to be started or something like that. What can happen in this case, or clear cache or things like that. So what can happen? Not just the profile is not just added through an interface, but we have a generic login listener interface and a common login listener class, which implements the login listener. the DI configuration passes in the composite login listener to profile. The composite login listener contains a list of login listeners, and also the DI configuration adds the booking class to the composite through the dependency injection. If you would like to go even a little bit more generic, then you can also use a message bus, so your modules can provide messages which the common module can distribute. So that was the anti-patterns and patterns I wanted to share you. And now, closing to the end of the presentation, I would like to show you an example architecture of an application. So this is something from one of my latest projects, but keep in mind that this is not a golden hammer. So I don't want to say that you should design something like this. Each application is different, but I would like to tell you how I came to this architecture. So this application was a large monolith application which we needed to re-engineer. And why I brought this up, because this is contains all the examples that I already told you in this presentation. So we needed to separate first the legacy and the revamp features. So this is like the border. We have legacy modules and we have the revamp modules. In the revamp modules, we wanted to make optimizations, and also because we had 6 teams, we wanted to assign each team, well, actually multiple feature modules to deal with. And therefore, we created the feature modules, and for the common functionalities, as I already said, we created new feature modules which are the common features, and they can be accessed through the API modules. Now, as you imagine, there can be situations that the API modules can have some common things, like data classes, like some utilities, some default implementations, things like that. And because of that, sorry, we also created these utility features. These are the bottom of the graph. And there was a gray area with some cases where we needed a wrapper around a third party, or a feature was just not worth the effort to break to API and feature modules. And for those categories, we created these common features type. So each of these types has rules. The app module depends on the feature modules. Feature modules can't depend on each other. Well, nothing can depend on each other within one row. And also, what I said already, the API modules can only depend on utility modules, and common feature modules can be only depend on utility modules. And these are enforced during build time, that nobody can make any exception from this. And with the legacy modules, we also made it separately, because when feature B, for example, went live and reached a point where we did not use again the legacy part, then we could just cross it out and delete the whole module easily. And also because we had much different quality rules for these. So in the legacy modules, we did not have detect because it was in Java. We did not have unit tests and so on. But for the revamp part, we had all the standard quality gates and code coverage and so on. So that is all I wanted to tell you. And do you have any questions? Yes, please.
Yeah, I have a question. How do you manage the common resources like strings, drawables? Do you throw everything in one module and then let others module pull it out, or you divide it per feature? What is your
Well, it depends on whether it's really common. So, like,
let's say they're not really common, but it would kind of easily manage it if you think that there is one place where you stash everything. I believe some material library did something like that.
okay, I see. So, for example, what you are talking about is put in this kind of common feature module. So, like a UI library, where you have some composables which are common mostly for the whole application, like a themed button or things like that. And also those fonts, diamonds that are used in everywhere. But for example, if we are talking about string resources, those are in the feature modules because they are obviously not common in any way.
Do you have a problem updating those? Because if they're in separate feature module, you need to set up CI somehow to know that they're the strings to be updated. Depends on the localization tool you use.
Yeah. So that's why I really suggest that this is not a golden hammer. So, for example, in this application, there are only 2 languages, which is quite easy to manage without any external tools. So we did not have any problems with that. But if, for example, this would be an application where this would be an interesting thing to handle, let's say, 100 languages, then obviously, most probably, I would find out something else.
Okay, thank you.
Any other questions? Yep.
Do you have some practice to avoid over-modularization?
Code review. Well, so you, yeah, that's it. So the situation is that usually it's quite visible when you create a new module, and if it's not obvious where you did it, then of course the reviewers will ask why you did it. And also, if it does not fit into the architecture, then you won't even have the ability to do that. So, but for example, you are talking about whether to start a new feature module just for a new screen, right? And if it has a good reason, then the code review, I think, is the best way to avoid unnecessary modules.
And how about old modules that were previously necessary, but over time, as things were moving around and being changed, they will be no longer necessary? How would you catch these leftover modules?
Well, you know, if something becomes unnecessary, then usually there is an event why this becomes unnecessary. So what I can imagine is like what I said, that because of some new features, we wanted to delete an old legacy module. That is an event that you are even preparing for. There are additional testings, you need to change the feature control and things like that. So if you do this, usually you can just add a ticket to the backlog that this is something that sooner or later we need to delete in a couple of sprints.
So basically, the developer who is working on the update has to catch that this module.
Not necessarily the developer. So if you imagine a large application, this is not driven by a developer. There is a release coordinator. There is somebody who sets the feature control. There are multiple sign-offs. So there are lots of stages where this can be code. So it's not like there is one developer and that one needs to catch. There are release pages. A couple of managers are involved. So well, in a large application, usually you have checklists to do before a release. So this kind of stuff can be coded by processes. Any other questions?
have you ever tried to separate tests, instruments tests and unit tests into different modules?
So the unit tests are, of course, separated into the modules where the code is. So the classes in feature A, the unit test that tests those classes is in feature A. About the UI automation, to be honest, with this example, it is even in a separate repository and not handled with the lifecycle of the application, but rather separately by even a separate team who works on those. But my gut feeling is that most probably those things can, if we are really talking about end-to-end test, then that can be live in the app module most probably, I guess. Because anyways, the original build time won't be affected by that because it's a different source set. So it won't spoil your build time. And anyways, for an end-to-end test, you need to build the whole set, I believe. I believe we are out of time, so thank you very much.